Hello, everyone. Welcome back to Ethics Seminar Series. This is John. I'm a seminar coordinator, and together with me is Kathy Menu. Kathy is our communication and IT specialist. Kathy and I will be today's moderator. And you can always check out our seminar schedule on our site or Google Calendar. And those links can you find in the seminar email announcement. The seminar is being recorded, and we will put the recording on as a YouTube channel. You are welcome to bring up any questions after the speaker's presentation. And today we are excited to have our speaker, Dr. Balaji, joining us from overseas. And let me give you a brief introduction about the speaker. So Dr. Balaji has headed the Modeling System Division at Princeton University's Cooperative Institute Modeling the Earth System since 2003. And he is an associate faculty in Princeton Institute for Computational Science and Engineering and the High Meadows Environmental Institute. With a background in physics and climate science, he has also become an expert in the area of parallel computing and scientific infrastructure. He is co-chair of the WTCM Infrastructure Panel, WIP, and is tasked with developing the scientific requirements for the global data infrastructure underlying the climate model in the comparison project, CMIP, a pillar of the IPCC assessment reports of the state of the Earth's climate. In 2017, he was among the first recipients of French President Macron's Make Our Planet Great Again award, marking the second anniversary of the Paris Climate Accord. He has served on scientific advisory panels for the National Center for Atmospheric Research, the Max Planck Institute for Meteorology in Hamburg, and is currently on the Science Review Group of the UK Met Office Petm Center. He is a sought-after speaker and lecturer and is committed to providing training in the use of climate models in developing nations, leading workshops for advanced students and researchers in South Africa and India. Dr. Balaji has a master's degree in physics from Indian Institute of Technology and a PhD in physics from the Ohio State University. Well, let's welcome the speaker, and I will hand this over to Dr. Balaji. Dr. Balaji, please proceed.
Thank you. I hope everyone can hear me fine. And thank you so much, John, for that kind introduction, and to John and Cassie Medley, who helped with a lot of technical issues. And John is going to be piloting the slides for me, and I will go forward. So thanks, everybody, for coming. So I'll be giving a kind of overview of where climate modeling, I believe, is heading, and because of some new developments in computing. And I phrased it in terms of I'm going to go a little bit into the history of how we got to our current state, which is why the title is Climbing Down Charney's Ladder. Jules Charney is one of the founders of our field, and this is about some of his work as well. So next slide, please, John. So the outline of my talk is to talk about climate science and climate models in particular. We'll talk about computational climate science, which is what I work on. And there is weather and there is climate. Quite often we speak about the two as though they're the same, but there is a difference. So in climate, we're looking at the radiative balance of the planet, over long periods of time, and how this is changing and the dynamical response. And then there is something when John von Neumann, who kind of was the inventor of the digital computer, first talked about forecasting the weather using computers. He also spoke about something which he called the infinite forecast, which is what we now call the climate, which is basically looking at weather over very long periods of time. So I'll go over the kind of a very brief history of computational climate science, how models have evolved from the early days to the current day. IPCC AR6 report has just been published. The model evolution parallels evolution of computing, and that computing is now hitting a kind of, just as, there is, we can talk about the climate crisis, there is also a computing crisis. There is a certain physical laws of building computers are changing. But the computers are, so it's not bad news necessarily. The computers are very good at some things. One of them is machine learning, and we can talk about how we can use learning to make our models better and what you learn from. And in summary, I'll try to show that this is the history of climate modeling. Had to make these choices about whether we want to do things from first principles or do we want to learn from data. So we're kind of going through a cycle, kind of inflection point or a cycle in this history, which I'll try to get to. So next slide, please, slide 3 and slide 4. So I'm going to talk about the climate science first. So this is yeah, good. You can go to slide 4. Thank you, John. Again, this is for if it's a broad audience. If everybody is a climate scientist, you know everything on this slide. So we say climate is what you expect and weather is what you get. Weather is what actually happens. But climate is based on your long-term experience of what you think will happen, and so climate is what you expect. So keep going down. Next. But when the climate changes, what that means is the expectations have to change. So NOAA publishes, NOAA's National Oceanic and Atmospheric Administration. They publish every decade what they consider to be what you expect, what the climate of the last 30 years is. Basically a 30-year average, the climatology of the last 30 years. And every few years, every decade, they release a new one. So they released a new one a few months ago. And you can see that if you look at the maps of the new normals are quite different, quite a bit warmer across the US compared to the old normals. So this whole business of what you expect and what you get, if it's changing, then you have to change your expectations as well. Next. And what we actually perceive is the difference between the weather and the climate. What I mean by this is that you can take a particular day's weather, and let's say if you're working in Fahrenheit, it's 70 degrees. If it is winter, you'll call it a nice warm day. And if it is summer, you'll say it's a very cool day because you're expecting a certain thing and then you're not getting it. So that's what you perceive. So when we say a day is a particular day is warm or cool, we're talking about this difference between the long-term statistical average and what actually happened on a particular day. So next slide. Actually, why don't you page through the next two more slides? Two more, please. I don't want to keep paging through this. Yes, let's stop here. So what we do is the weather is we consider, if you're doing the climate problem, weather is just noise. It's just day-to-day fluctuations. And then you remove it, and then you get to the climate, which is a signal. And you have to remember that these residuals are small compared to the observed quantities. So when we talk about climate change, we're talking about a change of 1 or 2 degrees over a century. But in a day, you'll get a temperature change which is much larger than that. So we are removing all these daily fluctuations, and you're looking at it's a small residual signal underneath it. And how this is built is based on a lot of different kinds of physics and chemistry. So there are fluctuations on all time scales and space scales. There are feedbacks, there are forcings, and there's very small things. Microbes can affect the climate. There are things that are going on, like collisions between raindrops can happen in a matter of seconds. And then there are also very, very long-term changes which endure over millennia, like what happens in the deep ocean. And when the continents, the tectonic plates move, that also changes the climate. So when you have changes, like for example, if you go back before 3 million years ago, the Atlantic and Pacific Oceans are connected through what is now the Isthmus of Panama. So when those two oceans got disconnected, the climate changed drastically because the water couldn't flow across. So these are all things we have to take into account when you're studying the climate. So if there are students in the audience, whatever subject you're interested in, any field of science and engineering, I just want to say that, there are lots of interesting problems for you in climate. Next slide, please. So this is the history of the climate. So I'm going to go through this very quickly. So this is 0 is present day. This is the climate average of 1960 to 1990. So this is if you see pluses, it means it was warmer than today. This is the global average temperature. And this is the time series going back 500 million years. And the left half is measured in millions of years, and the right half is measuring in thousands of years. So it's the scale gets more and more compressed as you go to the right. So you can see that there were these fluctuations, and then there were these very, very warm periods when what is marked, I'm unfortunately unable to point with my mouse, but if you look to the left, you see a thing called the PETM and the early Eocene Optimum. PETM stands for Paleocene Eocene Thermal Maximum. So during these periods, the weather was much warm, 14 degrees warmer than today, and the climate was totally different. The temperature gradient between equator to pole was very small. So you can find fossils of palm trees and dinosaurs near the poles because it was very warm back then. Then there is a slow long-term cooling getting down to present-day temperatures. And if you go now to the right half, to the Pleistocene and beyond, you have first a period where it is dominated by these ice age cycles, which is the ice sheets advance and retreat, and each time the ice sheet advances towards the equator, that means there is less water in the ocean, so the ocean level falls. And when they retreat, all the water goes into the ocean and the sea level rises. Then you get to what's marked at 20,000 years ago as the LGM, the last glacial maximum. That was the last major ice age. And now you're looking at a more compressed time series, and then you see it's a very interesting thing happens. So it warms up, it warms up, it warms up, and then suddenly around 10,000 years ago, the climate becomes very, very stable. And that stability is very important. So that's called the Holocene Optimum. And the reason it's an optimum is because it was stable. And if it is stable, that means you can expect from one year to the next that the weather will be the same. That's what makes agriculture possible. That's what makes human settlements possible. People could live in the same place for long periods of time. Before this, humans existed, but they were all nomads. So all of what we call civilization today, which is agriculture and human settlements, urbanism, all of that is based on this idea that the climate suddenly 10,000 years ago became very stable. And now if you go towards the very end, which is the projections towards the future, you can see that suddenly we are pushing the Earth out of this optimum. So that is the climate crisis that we're facing. Next slide. If you zoom in on this period, you can see there are different ways of estimating. So you may ask yourself, how do you measure the past temperatures? Because you don't actually have direct measurements. So we have satellite data, global data going back about 60 years. And then we have weather stations going back a few hundred years, which are direct measurements of temperature. Beyond all that, it's reconstruction from various proxies, as they're called, tree rings and ice cores for the most part. And you can see that there are these various features that you see, and there's a kind of period that in Europe was quite warm, as far as we can tell from tree rings. So it's called the medieval warm period. And then there is a cooling, which is called the Little Ice Age. They may have been regional. We don't necessarily know if this was a global signal. On the other hand, the current warming, which is the black line you see towards the end, that is very much global. It's just, it's increasing rapidly, and the temperatures are essentially rising everywhere. They're rising faster in some places and slower in some places, but they're rising everywhere. So next slide, slide 7. So one interesting feature is the link between CO2 and the climate. So that's what's the present-day climate has been shown very, very clearly that the increased CO2 from industrial emissions is what caused it. But there are some periods in past history where we can find similar things. So this is a reconstruction of CO2 from Antarctic ice cores. The Law Dome and the WA ice divide is the West Antarctic ice sheet divide. This is showing basically a decrease in CO2 levels in a certain period of history around the year 1600 Common Era. And that has been linked to basically the arrival of Europeans in the Americas and the conquistadors for first, and then the European and the English and French settlers, the Dutch, all of them came. Besides the fact of just they were kind of conquerors, they also brought pathogens with them that the Native Americans had no resistance against. So this paper estimates that actually this is one of the greatest human holocausts in history. Around 56 million people were killed. They made these estimates of how many people died. I mean, we had an agricultural civilization across what we would now consider the southern United States and Mexico, which basically disappeared. What that meant was that a lot of agricultural land, farmland and pasture land, became forest. And when that happens, what happens is the CO2 gets drawn out of the atmosphere. And so there is a dramatic global decrease in CO2 in this period. And the paper speculates that perhaps this could be linked to the Little Ice Age. So you see the connections. So there is the conquest of the New World, which leads to a massive death among the native population. And as a result, the agricultural land returns to forest, and that dying actually causes the Little Ice Age in Europe afterwards. Okay, next slide. So this is just the history. So now we'll get into the science. So how we get into this? So Eunice Foote, many people are, Arrhenius and Tyndall are often credited with this, but Eunice Foote in 1857, she did these experiments using basically glass jars, and she found that a glass jar filled with CO2 warms faster than a glass jar just filled with air. And she said that she speculated right then in 1857, an atmosphere of that gas would give to our Earth a high temperature. So the first time that somebody actually speculated about global warming. Next slide. And Bjerknes tried to actually approach it from a different direction. So he looked at, he was trying to, this painting shows that, he comes from Norway and the weather is, it rains a lot. So you can see the picture with the umbrella. So he was trying to figure out how to do this prediction, so modern weather forecasting. So there's an ironical story here. So he first formulated everything that we consider modern dynamical meteorology, what we starts with the primitive equations for the general circulation. So he discovered that in 1904. And his initial reaction, because that was the great age when physics thought that they could solve basically everything. It was just before, if you recall, 1905 is the photoelectric effect. So relativity and quantum mechanics comes right after. So right around 1904, physics was basically thinking they had solved everything. So he tried to solve the weather from first principles, and he wrote down the right equations for dynamical meteorology, but he could not find a practical way to integrate them forward in time. So he attempted graphical methods with hand-drawn contour maps. And then finally, he decides to go to empirical methods, which basically you have a lot of library of weather data, which is taken from stations. And then you draw contour maps by hand. Meteorologists draw contour maps. And then they have a library and they have memory and they have experience. And then they're able to tell when you see a particular weather pattern, how it will progress in time. So a historian called Nebeker, who wrote a book on the history of weather forecasting using computing called Calculating the Weather, he said the same person who invented dynamical meteorology ended up using methods that are neither algorithmic nor based on the laws of physics. He was doing forecasting basically by what today we would call pattern recognition. So you see, you're going to see the parallel between that and machine learning as we go forward. Next slide. So the Earth's radiation budget, I'm going to skip through these slides very quickly. So the Earth, the equator is basically where it receives most of the sunshine. So there's an excess of energy coming in at the poles. It loses heat, excess of heat coming in at the equator, and it's lost at the poles. So you're seeing the difference between the incoming and outgoing. So somehow energy has to be transported to the poles. Next slide. And if you solve that equation using Bjerknes' primitive equations, if you try to solve it, you come up with a circulation like this. These are all features we would recognize: trade winds and the westerlies and the mid-latitude jets that you see here. And there are a couple of cells which we call the Hadley cell, and the Walker cell is not shown here. But this is a fairly well-known phenomenon with the intertropical convergence zone, where there is when wind converges, it lifts moisture up, it makes clouds, it makes rain. So you see a green strip. And where the rising air tries to come down, moving more towards the poles, and what's marked as the high zones, you see deserts, because there the air is coming down and convection is difficult. Next slide, you'll see the same kind of circulation for the ocean. So you can again do the computation for the ocean by putting in the continents, and you'll come up with a circulation like this. So you'll see this: the red is the surface circulation, and the blue is the returning deep flow. So a lot of whatever happens to the surface can be transported into the deep ocean on very, very long time scales. And that's also, we'll see, it's going to be very important for the climate. Next slide. So we return to the computing problem. So Lewis Roy Richardson tried to say that, okay, I can take Bjerknes' equations and I can try to solve them. And this is an early method of what he thought he would do. So he would have a large number of people. There would be the calculators, and they would sit in various places, and then they would pass it would be like passing your boundary conditions, and you basically pass calculations from one person to the person next. And then there is somebody at the center who will shine a light and say, okay, now I want to know the result from you. And this is the way. So he actually tried to attempt it. He attempted it with 64,000 people. So it's a fairly, even by today's standards, a pretty large parallel calculation. But he failed. He completely failed because he did not know there were some basic laws of numerical computation. There is one in particular which was discovered in 1928, a few years after Richardson's attempt, which is called the CFL condition, which makes a numerical calculation stable. So since he did not have that, his calculation actually failed. So the first attempts to try to do this by computing did not work. So we returned to the weather forecasting the way Bjerknes did it, which is just looking at meteorologists looking at maps. Next slide. Then what happened was in the late 1940s, John von Neumann was a scientist at the Institute for Advanced Study in Princeton. He discovered this digital computer, so he could do the calculations. And the very first thing he wanted to do was to say, why can't we do the forecasting problem using this? So this is one of the early pictures. It's taken by Smagorinsky, who was the first director of the lab where I work in Princeton. The person on the left is Charney, whom I'm going to refer to a few times. The other people are also well known. Norm Phillips wrote on the first weather forecasting model. Smagorinsky, as I said, took the picture. So the digital computer actually transformed this whole game. So initially, they knew the equations. Bjerknes had written down the equations, but they could not solve them. There was no means to solve them, until the computer came along. Next slide. So this computer is called the ENIAC. It's the first one, and you can see that there were actually people who would connect the way calculations were done involved actually connecting one unit to another unit. So it was some of the computing is physical rather than, and then we went to punch cards, and then we get to the modern computer. So this whole thing. So you can see, and again, this is just a side point, but there were a lot of this work we know now. There's a lot of this uncovered history from NASA as well. There was a movie about people who did the computing. A lot of them were women. So and in fact, Clara von Neumann, who was John von Neumann's wife, apparently she was the one who actually taught Charney how to program the ENIAC. She was a hands-on programmer of the machine as well. Next slide. So then we go to what happens over the next 50, 60 years. So 1950 is ENIAC is the first calculation from which is Charney's barotropic vorticity equation is 1950. So from GFTL is a machine that was is a lab that was formed because of von Neumann and Smagorinsky, and they've been trying to work on this problem. It's one of the oldest climate labs. 1956 was the first computer they bought, the IBM 701. And I'm not going to go through the details of the slide, but you can see that the y-axis is logarithmic. So the power of computing has grown up not tenfold, but 10 to the tenfold. That's how much the computing has grown. And John von Neumann actually said that he wanted to look at the climate. What would happen if you took a forecast model and kept running it forever? What would it tell you about the long-term changes in the world's climate? And Smagorinsky took up the challenge, and GFTL actually has been working on it ever since. So that's the split between weather and climate takes place around this time. Next slide. So we'll go to what happened since then. So we've got now a lab has been set up. We've figured out how to solve these equations on computers. So we'll go into computational climate science. Next slide. So the first of these calculations that I find, really, this image on the right, which is it almost looks like an ancient totem of some kind. So it was the first Manabe and Bryan, Shukuro Manabe and Kirk Bryan at GFTL. They did the first couple model, and this is what it looked like. There was a very highly idealized land and sea, and it's it was only a sector. They didn't have the computing to solve the whole globe. And then there are some numerical problems when you get to the poles. So they removed the poles from their model, but they still did a very nice calculation. They showed that it was possible. You could solve the coupled climate system with both atmosphere and ocean and land. Next slide. That led to this one of the most cited papers in our field, Manabe and Weatherall, which is looking at temperature as a function of latitude, the mean temperature as a function of latitude. And what they showed, the dots are some observations. So if you use the known value of the atmospheric levels of CO2, then you see a certain surface temperature. This is temperature at the surface as a function of latitude. If you double the CO2 and run the same model forward for a long time, you see that you get the dashed lines, the temperature goes up by a little bit. And this will have very profound effects on life, on vegetation, on everything. So this was a very, I think it is perhaps the most cited paper in our entire field ever. So this paper gave rise to this idea. It was kind of alarming to think about the whole Earth's temperature changing as a result of CO2 emissions. So next slide. So we go back to Charney, and Charney was asked to take the results that they know and try to make a kind of assessment of what would happen under climate change. And he based it, so this is what we today would call the IPCC assessment report. You know, IPCC is the Intergovernmental Panel on Climate Change. So it was a very, I would call this the first of those. It was based on only 5 model runs, 3 from Manabe at GFT and 2 from Jim Hansen at GIS. And they basically said a few things that are considered very, even today. So they knew about the direct effects of due to doubling of CO2 is pretty small. It's 4 watts per meter squared. But there are all these feedbacks. There's something called the water vapor feedback. I'm not going to go into the details. The snow ice albedo feedback. And these feedbacks amplify the effects of CO2 until the warming is quite significant. The clouds are a big unknown in the system. They stated the cloud distribution is a property of the entire climate system. It's not just a local thing. So, and we don't know how the cloud distribution is the biggest unknown in the system. And they came up with a range of what they call the surface warming for doubling of CO2 to be in the range 1.5 to 4.5. That estimate has really not been much improved ever since then. So the Charney report is 1979, so it's about 42 years ago. It's still a pretty good estimate, even all the way to AR6. Next slide. This is still taken from AR5. I couldn't find an equivalent diagram yet from AR6. I probably should look a little harder. But this is basically, the numbers here, which are 42, 39, and 32, that's what I want to point to. So initially, there were just 2 models, the GIS model and the GFTL model. Nowadays, you have lots of models from all over the world. In the latest AR6, you have close to 80 models or something like that. So this famous figure from the AR5 report, which is from 6 years ago, it shows the historical temperature change on the right. 42 models have performed that experiment. And they're looking at 2 scenarios going into the future. One, which is called the RCP 8.5, which is essentially don't do anything about climate change. And that shows warming going up to 4 degrees with a spread around that. And then 2.6, RCP 2.6 is one where there is some emission controls. And there you can see that you can stabilize the temperature about 1 degree above today. So, and now AR6, there are more models, and there are India, China, Brazil, Korea. There's many, many models from all around the world. So this is what the assessment reports have become. So this is the whole kind of very quick history of how computers have transformed climate change studies from the beginning until today. Next slide. And the models keep adding detail. So the detail comes in 2 ways. One is you keep adding resolution. You can see the pictures on the left show how in the far is the first assessment report, second, third, and then AR4. You can see how the resolution changes over time, adding more and more detail. And on the second right, you can see all the processes that we include in the model. So that's what I call complexity. The model's complexity also increases as we keep it. So initially, the mid-70s model had basically clouds, rain, and CO2. And then you added land surface, then you added other things, sulfates, and it keeps going on like that. So we keep making it more and more complex. So today, a typical model would have 25 to 100 kilometer resolution, and it may have 100 different physical variables that you're trying to simulate. So these are very, very complex, and you keep adding details. So how can you do that? It's because of the history of computing I showed you, because computing power has increased logarithmically over 10 orders of magnitude. So you can add resolution, and you can also add complexity. Next slide. And you can do what's called attribution. So this is a very important part of climate science, which is because we are using computer models without experimenting on the actual Earth, we can remove and add certain processes and see how they affect the climate. So this idea that you can create counterfactual Earths is very, very important in the history of modeling. So this study is historically the Indian monsoon. This is showing the trend over time. It slowly weakens over time in the data going from 1942 to present day. But if you look at if you have only CO2, which is here is called well-mixed greenhouse gases, it's the purple line WMGG, it will actually show warming. So if CO2 is showing a warming, why is it cooling? Then you add another effect, which is aerosols and natural forcing. So you can keep adding them one by one, and then you can say, which effect is actually causing the weakening of the monsoon. So this is what I call data from alternate Earth. So the scenarios are data from the future Earth. It doesn't exist yet. You don't have observations. So we rely on models for both of these things. We rely on models to kind of get us so-called data from the future by simulation, and also from counterfactual Earths that don't exist. So for both of these, we need the models. Next slide. So what happens in computing? So this is an old slide. I just put it here for a joke. So this is the first attempt at parallel computing was called, was pioneered at NASA. And this is the website I found when I was looking for some slides, which they call no-cost parallel computing. The parallel computing became popular because computers have become kind of an everyday item. Everybody had a PC in their house, and you could just wire a lot of them together and make a big computer. So they called it no-cost parallel computing. They basically take a lot of old computers, which people are going to discard, and then they wire them together and they make a parallel computer. So they call the price-performance ratio, which is the price is zero, so the performance is whatever you get, and you get like, zero price. The performance per price is infinite according to them. It's just a joke, but anyway, the parallel computers were very powerful. We all learned to use them really. And they got very good, so we were able to use them for a long time. So next slide. So why did just regular everyday machines get faster and faster? This result comes from a physical law which is called Dyna Scaling, which is based on the circuit that we use, which is CMOS, which is a way of etching circuits into a silicon substrate. And what this shows, this Dennard result from 1974 shows that if you keep miniaturizing this is what all of this comes from. All of this increase in speed comes from the fact that you can etch these wires finer and finer. So each time you etch it finer, if you reduce the scaling of a transistor by a factor kappa, then you see that the voltage goes down by kappa, the current goes down by kappa, and everything scales downward. One important thing is the second last one, the power dissipation. It goes down by 1/kappa squared. And if you divide it by the area, there is no change. So what it means is that you can keep making transistors smaller and smaller, and the amount of power it will take will keep remaining the same, but you'll get, but the number of transistors will go quadratically. So this gives rise to what's called Moore's law, which is why you get all this exponential rise. You can keep making these things. People keep learning how to fabricate transistors smaller and smaller, and without changing the power requirement, and while increasing the speed quadratically. So that is, Dyna scaling gives rise to what popularly is known as Moore's law, which is that every 18 months, the transistors will halve in size and the computing power will double in size. Next slide. What happened in the last decade was that, yes, you can keep making transistors, but you could not make the arithmetic go faster. So the most important thing to look at is the green curve here, which is the frequency in megahertz, which is the speed of the clock speed of a arithmetic operation. Each tick of the clock, you get a new update of all your computations. That has basically stagnated for the last 10 years. So it's been around a gigahertz, and it's still around a gigahertz for many, many years. So what this means is that you can do a lot more arithmetic, it's true, but the arithmetic is not getting faster. You can do the arithmetic at the same speed, but you can do many more calculations, which means that the models have to become more and more and more parallel. That's the only way you can do it. So next slide. There is a problem with the way that fluid dynamic codes are created, which is you cannot make them parallel beyond a point. And that is shown in this slide, which is called a roofline diagram, which is that in order to do a calculation, you have to get the data into the memory. And so you're dependent on both things, the memory speed as well as the speed of the computation. So operational intensity is measured in flops per byte, which means how much arithmetic can you do each time you move a word off memory. And there are some codes which are very, very high in operational intensity. But our codes are what is you can see almost at the left of this curve, which are called stencil codes, which means that each point is dependent on only its nearest neighbors. And those ones, you have to move a lot of data in order to do a computation. So because of that, you cannot actually keep up even with the speed of the computer. So you're always going to be slow. Whereas there are other methods, and deep learning is one of them, which actually can take advantage of all of these things. But we have a problem in the way fluid dynamics is computed on, it's done on a computer, that we cannot make the codes run as fast as we would like. Next slide. So today, when we look at the what's called the exascale roadmap, the next machines that are going to come out over in 2021, 22, and 23, all of these machines, they're from various computer vendors. You'll see NVIDIA, AMD, Intel, all these things, but they all have what are called GPUs, graphical processing units. And they were first used for graphics, that's where the name comes. So basically what they're good at is doing a lot of arithmetic in parallel. So, so that's what these things are good at. Next slide. Europe and Japan are moving in a different direction with another chip design, which is called ARM. And one of the advantages of ARM is that its power requirements are somewhat lower than some of the chips we're talking about. But again, we're talking about doing a lot of arithmetic in parallel. So this GPP stands for General Purpose Parallel Family. So everything is going to be the Dennard's law is a physical law. You cannot design your way out of it, at least not with silicon. Next slide. And so what's happening is that the HPC is generally graduating towards machine learning. So this is showing from NVIDIA what they're investing in. So HPC, which is what we would consider computing, which is what their investment there is about 4 billion. But what's called DL training and DL inference is deep learning. They're investing an order of magnitude more money in that stuff. First of all, because there are a lot of very, very good applications of deep learning. You know, everybody knows about self-driving cars and image recognition and so forth. There are also some implications of some applications which are kind of scary, which is facial recognition and so forth. But in any case, there's a lot of interest in it, for good or bad. Next slide. I'll skip this slide. This is just showing that the cost of data is actually stabilizing for various reasons, but this is not relevant to this talk. Next slide. So if you start getting these GPU type machines and you're getting to an exaflop, what are you going to do with that? So this is a paper which is trying to show what you can resolve at an exaflop. And what this is showing is that you can get to resolutions of models around 1 kilometer or so, but you can only run them on a whole machine. You can maybe in a year you may be able to. If you want to run 1 year per day, you have to do a lot of improvements, and we're not very clear where they're coming from. So this is going to be difficult to run it directly. So next slide. And you have to also take into account the energy cost. So this is just to introduce a project where for CMIP6, we are trying to measure how much energy was used to do the simulation. So we have to take both of these things into account. Next slide. So if you run all these models, so the question is, these are a bunch of models running at very high resolution, and one of them is a satellite image. So you heard of the Turing test, which is how do you tell a human from a computer by conversing with it, which is what Alan Turing proposed. A similar thing for climate would be to look at some images and say which one is a satellite and which one is a simulation. It's becoming hard to tell. That's a fact. Next slide. But we cannot run these machines long enough. So what we're trying to do now is to take this deep learning. So take a look at this deep learning, and I talked to you about how many operations per memory. So in a deep learning network, you're basically, instead of going from your red inputs to your blue outputs directly, which would be what we call regression, you try to put a hidden layer of what are called neurons, and you can put as many layers of neurons as you want. And each of these black lines represents a computation. So here you can see that as you keep increasing the number of neurons, the number of computations actually increases quadratically. So this is actually ideally made for today's computers. So deep learning is a great application. So a lot of us are trying to change the way computing is done to see how we can take advantage of these kinds of algorithms. Next slide. So what ML is trying to do, machine learning or deep learning, it takes something, in this case, let's take images. It tries to reduce them to a fewest number of things which they call features. And once you get to a very small set of features, you can create, using those features, new faces. So for example, you can take two faces here. You can see a face from the left of the screen and the right of the screen. And you can say, you can create a new synthetic face which looks, 0.3 like the face on the left and 0.7 like the face on the right. And you'll get a new face out of it because you created the essence of what a face is. So the similar thing for our field would be you take a lot of data that's coming from the ocean and the atmosphere, and you try to reduce it to the smallest number of features that describe what the data is. And that would be like trying to discover the physics of the model. Trying to say, so if you have lots of data, then how do you actually find what is the simplest physics I can use to describe this model? And can we do this using machine learning? Next slide. So what we try to do is we try to coarse grain the model. So you take this high resolution model that I showed in the Turing test, and you say, if I wanted to actually coarse grain it down to a low resolution that I can actually run easily on a small computer, I have to discover everything that's going on the fine scale, in this case, clouds, and you try to understand that. So I've given you a list of a few papers where people have tried to do that. You take your global cloud resolving model and you try to learn everything that's going on in the small scales, and you try to use that. So this is exactly the ML approach. You try to reduce a complex data set to a small number of features. Next slide. And this, again, I'm going to skip the slide. So there's all kinds of uncertainty in the model. So one thing we have to keep in mind is that you cannot just take historical data and try to learn from that, because the future is evolving in strange ways. And I also pointed out we need counterfactuals. So this is an old figure that's shown a lot. It's conceptual. It's just showing that there are different kinds of uncertainty. We don't know what's going to happen in the future. That's the green part. That's the scenario uncertainty. There is what's called structural uncertainty, because we don't understand the physics fully yet. That's imperfect understanding. So we have to be able to span all these kinds of uncertainty. So simply relying on one observed time series of data from the last 50, 60, 100, 200 years is not going to be good enough. So we have to learn from physics that includes counterfactuals, things that have not been observed. So next slide. So we tried, and the other important thing is that observations also can be a little tricky. So this is a very interesting paper. I don't have the time to go into it in great detail, but it's looking at the strength of what's called the Hadley cell circulation. And the blue is from all the models that are used in the CMIP, in the IPCC assessments. And they're all showing that over time, over the next century, this century rather, the Hadley cell is going to weaken. But a few forecast models, which are the ones shown in green, they seem to show it increasing. And the thing is with observations, if you can take them from different sources, they're not necessarily coherent with each other. Whereas the models, because they're physical models, they try to make everything, they conserve quantities very exactly. So the paper concludes that actually it's very likely that the models which are shown in blue are correct, and the Hadley cell is indeed weakening, even though some of these forecast models say they're strengthening. So again, this is another reason for saying that we cannot just rely on observations to train on. If you're going to do machine learning, we have to learn from very good models. So we need both of those. Next slide. And the other thing we have to worry about, again, is to point out probably reinforcing the same fact. The climate is not stationary. So if you learn from historical data, you get these errors. So this is a paper where we showed that if you're learning from this is statistical downscaling. It was not called machine learning at the time, but basically if you're learning from this blue histogram, which is the temperatures of the present day, and you try to project to the future, you'll make some errors, because in the future you're going to get a histogram of temperatures which is moved to the right, and the training data, the machine learning algorithm will never see from the historical data. It will never see the data that's shown in brown, and therefore you will not learn it correctly. So you have to be very careful about making sure your training data is good enough. Next slide. Again, this is the paleo problem. I'm not going to get into that in the interest of time. But I'm willing to talk about it later. The models are not very good at doing paleo. So again, if you just do learning on present-day climates, you're not going to be able to understand what went on in past climates, and which means also has implications for future climates. Next slide. So the problem with the models is that we are doing this truncation of the model. We cannot compute them to infinite resolution, so we're truncating them somewhere. And when you do what the slide is showing is that the flow of atmosphere and ocean is basically turbulent. At very large scales, it's two-dimensional turbulence, which has a slope of k to the -3. This is showing the wavelength in kilometers on the x. The scales are in thousands of kilometers. When you get down to hundreds of kilometers, down to 1 or even less than 1 kilometer, down to tens of meters, you have this three-dimensional turbulence. And since you cannot resolve the whole thing, you're truncating it somewhere and you're trying to learn the fast scales. Next slide. When you're doing the learning, because you're doing the truncation, you again have to be careful about whether you're learning how this model will behave under different conditions. So I'm just repeating a point which I made earlier. So this again is trying to learn the temperature distribution that a parameterization is giving, which is trying to represent all the scales that I showed on the previous slide, which you cannot resolve in your model. If the climate is warming and they're trying to learn what a model is doing, they're trying to basically emulate a model. If you train on B on the top right, which is on the combined climate, using the warm and the cold climate, it does a pretty good job. But if you train only on the control climate, which is the present day climate, it doesn't do a great job. It does a very poor job, in fact. So again, this is emphasizing the point that your training data has to, for machine learning, has to encompass all the cases you want to see. Next slide. And this is taking the new approach of not just learning what it is doing, but actually trying to learn the physics. So these are a couple of interesting papers where they're trying to learn what is happening in turbulent flow in the ocean. And if you cannot train on all the data, you train on only a subset of the data. You better make sure. So they use 3 different areas of this simulation to try and do the learning from. If you learn in the area on the top left, which is zoomed out, which has all the interesting physics with the jets and all that, it does a very, very good job of simulating what's going on at very fast scales in turbulence, so that you can then reproduce this simulation without running at very high resolution. Next slide. But when you get to very, very large scales, and then this becomes when we try to do this for the Atlantic Ocean, we have some difficulties as well. So this is just illustrating the problem that you can do this sometimes in very idealized models, but it's harder to do it in the real ocean. Next slide. So what people have been trying to do is to actually try to see if they can get the physical form. They write down an equation of the result instead of just doing a neural network that fits the result. So this is again an interesting paper from 2009 where they tried to learn Newton's laws by looking at data from, you can see there's a double pendulum and a weight connected to 2 springs. So if you're familiar with classical mechanics, these are your problems. So based on these equations, they're actually able to recover Newton's law. They're able to discover it directly. So they're actually discovering the form of the law from experimental data. Next slide. And this is similar experience with Navier-Stokes. I've just given all these slides with the links there so that people can actually, the slides will be distributed later. If you're interested in any of these results, you can follow along. So again, this is showing that they're able to discover, they write down Navier-Stokes from data, they're able to actually derive and write down Navier-Stokes equation as it is shown in the box called D on the right. So they can actually write down the equation correctly. Next slide. And similarly, they've done, so the paper I showed on the turbulence in the ocean, they were able to show in this slide that they were able to discover what is the form of turbulence that's happening at subgrid scale. And what they showed in this result, what this is showing is that they're able to, so here the cyan line on top is the actual evolution of kinetic energy. And if you try to do it at very low resolution, you get the gray line on bottom. So basically, you're missing a lot of the kinetic energy in the ocean. So they tried various learning methods, and they showed that they can derive a parameterization of subgrid turbulence, which actually looks like that somebody else had derived in a previous paper. So they're actually able to derive the equations directly from the equation. So next slide. So next, and I'm going to the last slide now, so then I'll stop. So I'll talk about what this means by, I've run through a lot of data, but just to give you a flavor for what it is we're trying to do with machine learning. So Charney, when he developed this model, he wrote a model which had only one vertical layer. So, and it was called the barotropic vorticity equation. He said that as computers get bigger, we will climb the ladder of complexity. So and then Phillips made a model which had 2 levels. So that was the next model, and it made very, very accurate forecasts. And then now we have very, very detailed systems. But the problem is the models have become so complex sometimes so there is Lewis Carroll wrote this story called Sylvie and Bruno, where they talk about maps. And Borges is another author who wrote a similar story. But they're talking about going on a hike, and then one of them says, well, I have a map of the countryside that's 1/10 the scale of the countryside itself, and it's a very big map. And the other one says, oh, I have one better than that. So I have a map of the countryside which is 1:1. It's exactly the scale of the countryside itself. And so the first one says, can I see it? He says, well, no, it's too big. I can't even unfold the map. So you see where I'm going. So the models are becoming so complex that just because you can simulate many things, it doesn't mean you actually understand what's going on or you can actually use it. So the question is, if you have these AIs that simply do not tell you what's going on, but they tell you, trust me, I'm giving you the right prediction, would you trust it? And the reason why I say you shouldn't do that is because you have to be able to go outside the bounds of your observation. You have to be able to generalize. So what we want to do is to derive hierarchies of simple models. The complex models are great. They give you a lot of the detail. They're very, very useful. We cannot learn only from observations because our observations are too sparse. So we need the models. But we have to learn from them, and we cannot learn black boxes. We have to learn simpler models. So this is what is called the model hierarchy. So when I talk about climbing down Charney's ladder, what it means that you develop all your very complex, very high resolution models, but you try to learn simple models, because that's really what we need in the end. So that's my survey paper called Climbing Down Charney's Ladder, and I'll leave it at that and open it up to questions. Thank you for listening.
So we will now take questions. So if people could raise their virtual hand, you can do that by expanding the, I think it's the attendee panel, and there should be a little hand, or you can just type in the chat and I can unmute you so you can ask a question. We do have a question that was a few minutes ago from David Wynn. David, I asked if I could unmute you. You haven't responded. I don't want to just unmute you without permission. I'll just read his question. He says, and David, if you want to be unmuted, you can just let me know. He says, how are the models going to correct or take into account for all of the industrial chemicals, current and new chemicals, being added to the atmosphere and the oceans? What about ozone layer damage and other atmospheric damage we do not realize yet?
So we are, there's an observational community which is going very hard at this problem. So they're inventing always better methods of observing remote sensing emissions of different kinds. So we have a pretty good inventory of various kinds of emissions. There is a new series of satellites that have gone up, and there are still more in the plan. There is something called the OCO, the Orbiting Carbon Observatory. There are various kinds of emissions which we are measuring from space, and the question. So I think the observational knowledge is whatever we're able to do, we're actually doing it, and that includes. You mentioned the ozone hole in particular. So we are measuring what is happening to the ozone hole. If you're talking about policy, the Montreal Protocol of the 1980s is actually one of the success stories where we successfully were able to taper and reduce the emissions of CFCs, which was causing the damage to the ozone hole. And they're monitoring ozone very, very closely to see how the pace of its recovery. So yes, a lot of the pollutants are being measured both locally as well as globally through remote sensing.
Thank you. We have a raised hand from Thaddeus Komasek, who is now unmuted.
Hi, yeah, thank you so much. That was an excellent talk, and it got me thinking quite a bit. I really enjoyed it. I just have a basic question about kind of the universality of deep learning for understanding climate. I'm wondering if, developing more robust, model hierarchies from complex parameterizations for deep learning, if that will simply help us understand Earth's climate and Earth's climate dynamics, or if there's a way to also better understand geophysical fluid dynamics more generally.
Yeah, so that's a good question. So it relates to the generalization problem. So and there is a beautiful and famous essay written by Isaac Held, who retired from my lab a couple of years ago, which is talking about the gap, what he calls the gap between simulation and understanding. And that's getting to the problem that you're talking about. So you can, if you you can simulate things exactly by just trying to mimic what they're doing, but then it won't generalize. So the question is, if I wrote down equations of GFD, as you say, geophysical fluid dynamics, then I can ask questions. For example, what would happen if the continents were in a different place from where they are today? So that's one of the problems I tried to bring up. Or you also try to test these models on different planets, right? You run the same model and you run it on Mars, or you run it on Titan or Jupiter. So I mean, obviously you have to change some of the physical constants for those models. But if your model is good, it will generalize to a lot of cases. Then you will learn to trust your model. So I mentioned the word trust in the first bullet here. Why would you trust a model? And it's because you can either try to put it through various things and extremely a series of tests, and if it passes all of them, and it also has to have fidelity relative to other ways of looking at the evidence. So there's been some recent assessments of the Earth's climate. There was a paper by Sherwood et al., which took a lot of years to produce, where they've actually tried to say this question of CO2 and climate sensitivity, using all lines of evidence that we have, not just models. What's the best assessment we have of climate sensitivity? I showed you in the Charney report, he's at 1.5 to 4.5. And if you look at AR6, it says something very similar. But they try to go beyond models, and they try to include many, many lines of evidence. And paleoclimate is very, very important, because that's the question you're asking. It's how would this model behave if the conditions were extremely different from today? And so, yeah, we need all of these things. And for that, how you'll do that with machine learning, I believe, is that if you can actually derive simple models. I think otherwise we will be just mimicking what's going on, and without actually knowing what's going on, then trust would be much harder, because you wouldn't know what would happen if there was some major change, a tipping point in the system. Does that answer your question more or less?
Yes, thank you. So climbing down Charney's ladder will lead to the generalization inherently by better understanding the underlying processes.
That's the way I'm looking at it, yes. Yeah. Thank you.
Thank you. We have another question from Thomas Shore, who is unmuted.
Hi, thank you very much for this, frankly, very enlightening talk. And I'm here the thing I'm wondering here while you're talking is, how much of a problem is it that these deep learning algorithms don't have an understanding of basic physical laws? At least that's what I think they don't. For example, they don't know that energy needs to be conserved, or that mass needs to be conserved. Like, is that a problem?
Yeah, so you can do two things, right? So you can either tell that energy must be conserved, so you can make it a constraint in your learning directly. So that's one way to do it. So you can use, so in optimization, you can apply these things called Lagrange multipliers, which you can put a constraint and you can give a certain weight to it. The second thing you can do is you can start with a set of variables where, so if you write down the equations correctly, then energy will automatically be conserved. So let's say you knew kind of what the form of the law has to be, so that you're writing down Newton's law, which has, one of Newton's laws is that energy must be conserved. So if you write it down and Newton's laws in what's called the Hamiltonian form, energy is automatically conserved in that. So so if you knew what basis, what variables to use for your problem, you can enforce certain kinds of conservation. But so we will try to do that. So we do not want to violate basic physics, and there is a problem. So in some of the early papers that I'm citing, which even some of the ones I've cited in this talk, which you can look at, energy is not conserved, and they had to in that Bolton-Zana paper I showed, for example, momentum is not conserved. And they were able to correct it in the next generation because they were able to switch to using a different form of the equation in which momentum is automatically conserved. So that is what you're putting your finger on as the basic problem. Machine learning doesn't necessarily know anything. It is basically saying input to output, what is the most efficient map? That's all it's doing. And so you have to make sure that you give it all the data that it needs to have. And that includes data about conservation laws, basic constraints.
Okay.
So yeah, I mean, this is one of the key issues. Yeah.
Thanks.
We have another question in the chat from Kyle Dedrick. Didn't respond to my request to be unmuted, so I'll just read it out loud. He asked, if one were to plan a voyage across the melting Arctic next year or the year after, is it better to rely on historic sea ice data or a climate model that predicts the ice cover, since the sea ice histograms are changing, driven by climate change?
Yes, so that's a an interesting question. So the models, to my knowledge, have not done a great job of predicting the retreat of Arctic sea ice in the summer. They're under-predicted. It's in the last 20 years of data, it is happening faster than if you take a lot of the models and look at all their predictions. It may be getting a little better, but a few years ago at least, the actual rate of decline of Arctic sea ice was faster than any model was predicting. So in answer to your question, the models are not yet good enough to do the problem you're asking. The historical data is obviously not good enough. So what I would do is to do what Bjerknes did, which is to just look at the data and look at just do a trend based on the actual data and use that for prediction. So so this is what Bjerknes did. He discovered the physics. He didn't know how to use it to actually do computation. So he said, okay, I know I'm happy I discovered the primitive equations, but I'm going to put it aside because I want to forecast the weather, because in Bergen it's raining. So I think we would have to do the same if you wanted to sail across the Arctic next year. I would just rely on data and extrapolation. Machine learning does not do extrapolation well. Let's make it clear. Machine learning is basically an interpolator.
Thanks. That's actually it for my queue. Does anyone have any other questions? You can raise your hand. You can type something in the chat. Do you have any last-minute questions for Dr. Balaji before we conclude today? I'll give you like 5 seconds. Oh, yeah, you can do that. So Thomas Shore, you are unmuted again.
Hi, sorry to ask another question, but I've also something that's been in the back of my mind here while you were talking is that you said the computational intensity of CFD calculations, because of the way the stencil is and everything, is very low, right? If I remember correctly, yeah, compared to machine learning.
That's correct.
Which means that for the same amount of data, machine learning can do extra computations, and the assumption here is that would lead to a better result. But is that always the case? Like, are those extra computations that it does with the same data in memory improving the result necessarily?
Yeah, because in the end, what will happen is that there's two phases when you do the learning problem, right? So the first phase is the actual learning, which is given a lot of input data and a lot of output data. You learn the network, you learn the mapping in between those things. So that is called the training period. The training is very computationally intensive. But once the training is finished, the next stage, which is called inference, it's actually extremely cheap. Okay, because you've computed all the weights of all the neurons. Now you just have to do a series of multiplications to go directly from your inputs to your outputs. So that can be done extremely cheaply. So the cost of inference is very low compared to the cost of training. So it's a roundabout way of answering your question. So I think you're doing a lot of computing. Hopefully that you're extracting a lot from the data. So you're finding it's learning how to ignore the noise and find all the correct patterns that underlie the data that you're looking at. And then afterwards, you can execute it very fast once it's discovered that. But again, I would return to the idea of the hierarchy of the model. It would be much more satisfying if you actually could say that underneath this data, there is, instead of just saying inference is fast, training is hard and training is expensive and inference is cheap. Finding the simple model, that's actual learning, whether it's by human learning or machine learning, finding the simple model is hard, but once you learn the simple model, you can execute it very easily. So I think that's really what we want to go towards. And then you don't have to worry so much. Then you're running simple models. You don't worry too much about the computing cost. They'll run on anything. They'll run on your phone, for example. So
I see.
it's a way of answering your question. So I mean, the machine learning is basically trying to fit a lot of parameters to fit your input to your output, right? I mean, it's trying to find all the weights of all the neurons. Each one is called a parameter. So so it's fitting a lot of parameters, but it can be better because so long as you do it correctly, so long as you don't overfit and just try to, every little wiggle you don't want to reproduce it, because most of it is, a lot of it is noise. So you have to learn to ignore noise and only focus on signal. But if you do that correctly, we're using this approach that I'm calling climbing down Charney's ladder, then I think you can learn something that can execute very well. I think I don't know if I answered exactly the question you were asking.
Okay, no, that makes a lot of sense. Thank you very much for the answer. It clarified things for me a lot. Thanks.
Thank you.
Thank you, everybody. I assume if you haven't raised your hand by now, you don't have any more questions. So thank you, Dr. Balaji, for giving us this great talk. And thank you, everybody else, for showing up to our first seminar of this semester. It's a pretty good one to kick it off. So we will not be having a seminar next week. I believe we will have one the week after, but John can correct me if I am wrong. Please look at the seminar schedule. And thank you, everybody. See you later.
Thank you, Kaz and John, for all the technical help and setting this up. Thank you so much.
Yeah,
Thank
thank you for being so patient.
We'll send you the link of the video recording soon.
Yes, thank you. And again, as I said, if anybody, you are free to distribute these slides to anybody. So.
Oh, sure.
Great.
Yeah.
Great. Okay, I will end the talk now, but have a good day, everybody.
Thank you. Bye.
Goodbye.
Bye-bye.